Good morning, everybody, and welcome back to MAE 760 Engineering Analysis 1. So last time we finished the vector multiplications, and today lecture we are going to start the same topic, but we will continue in defining the equations of line and plane based on definition of vectors. I want to remind you that homework number 1 is now published online at K-State Online. The homework will be due by Monday, the 12th of September, which is 2 weeks from now. Again, you have to abide by the rules. The first one is the write-up rules. Look at the write-up rules and just write the homework according to the rules. Also, you are more than welcome to work together in the homework, but again, there is no cut and paste or copy from your friends. So this is the 2 comments that I want to tell you today. So let's start. So today's lecture is just equations of line, planes, and spheres and their applications. So we'll start first with equation of line. So we have several definitions for the equation of line. Let's assume the first one is line passes, if the line is passes through point. So let's assume that we have a line like this and a point on the line A, and the position vector for this point is just vector A small, and the origin is at O, and the direction for the line is just vector B. And then let's assume that there is any point R on the line here with a position vector R dash. So this point R is at a distance lambda from point A. So you have a point A and a variable distance lambda from point A. Lambda might go from negative infinity to plus infinity. So A, R, those are the position vectors for points A and R. B is just the direction vector for the line, and lambda goes from negative infinity to infinity, and it is just the distance from A to R on line. Now, how can we represent now the equation for line? Very simple. R is just equal to vector A plus lambda multiplied by vector B. So this vector R, if you go from here to here, then from here to here, This will give you the vector r. And again, vector b, if you multiply it by this scalar quantity, will give you the position of vector point r with respect to point A. So this is just this is just the equation of line. So this is one form of representing equation of line. We might call it one. So if A equal to 0, this means that R will be equal to lambda B. So if you just shrink this until it becomes 0, you are on the line here. So the equation of the line, the origin, will be here, and the equation of the line will just be lambda multiplied by B, because you will be on the line. Now, we can again take this one equation, simplified, and it will be lambda multiplied by B, again R minus A divided by B is equal to lambda. And then you can define the equation of line in terms of the component of this equation. So the components of R is just x in the I direction, y in the j direction, k and z in the k direction. So this will be x minus component in the x direction for A is ax divided by bx, and this will be y minus ay divided by by, and again this will be z minus az divided by bz, and all of this will be equal to lambda, or in this case lambda is constant, so it will be equal to a constant. So this is again another representation for the equation of line. So if we take B cross B, what's the value of B cross B? 0, because the line is, you take the line in itself, and in this case the angle is 0, so sine 0 is 0. So you can take this equation here, or this equation here, and you just cross it with B, and this will give you R minus A all crossed with B is equal to lambda B crossed with B, and this will give you 0. So this is again a third representation for the equation of line. Just R minus A crossed with B is equal to 0. So what if we have, this is just a line that passes through a point A and it has a direction of B. So what if we have now an equation of line, but the line equation, the line passes through 2 points, fixed point now, through 2 fixed points. And instead of just one fixed point, and it can go anywhere from negative infinity to plus infinity. Now what's the equation of line? If we have the line passes through 2 fixed points, this point and this point, and this is the origin, and This is the position vector for point A, and this is the position vector for point C. This is the origin, and this is C, and this is C. In this case, we will have, let's say, any point R in between A and C, and this is just the position for the point R, and this will be the vector from here to here is just A, C, and it is equal to what? AC? C minus A. So this will be lambda multiplied by C minus A. So this is C. If you subtract A from C, will give you this vector AC. And if you take just this segment, you will multiply by lambda. Lambda in this case will be less than 1. So did you have any question regarding this? So again, the equation of line in this case will be just this point R is equal to the vector A plus this vector lambda multiplied by C minus A. Any questions so far? So let's go now and define the equation for a plane. So just we give all the representations, possible representation for equation of line. Let's look at all possible representation, vector representation for equations of plane. So now equation of plane. Again, as we described here for the equation of line, we said that we have two situations. The first one is you have a point on the line, and then you have an extended length of the line, or you have 2 points on the line and you want to define the line. We will have exactly the same. We will have 1 point on the plane, for example, and a perpendicular to the plane, or we have 3 points on the plane. So the first case is plane will be passing by point A with a position vector A, and the plane is perpendicular to a unit vector N. This is unit vector. So let's assume that this is the plane. Then let's assume that this is the unit vector to the plane, and it is perpendicular to the plane, and this is the origin here. And let's assume that the point A is here, and the position vector for point A is just vector A, and there is any point R. So this is a fixed point. R is any point on the plane. You can move R around in the plane, but this is a fixed point, and the position vector for the point R is just R. Now we'll have another distance here. So what's the equation of the plane? What's the vector? R minus A. So this is R minus A will give you a vector R minus A. So this vector is in the plane. Do you agree? Because both points A and R are in the plane, so the vector R minus A will be in the plane. Then if this vector is in the plane and this vector excuse me, is perpendicular to the plane, what do you think the equation of the plane will be? Cross? Do you think is it cross? Dot product. Why? Because if I dot product R minus A dotted with normal will give me 0. But if I cross R minus A with N, I do not know what's the vector. It's not 0. So this is the equation of the plane. And now you can use the distribution property to say that R dotted with N will be equal to A dotted with N. So same representation. Okay? And what's A dotted with N? Let's look here. A dotted with N. So let's take the direction of N like this. And this is A. And this is just this line from here to this point. So this is the direction vector R, and this is in the plane, and this is the direction of N. So A dot N is just this distance. Yes? Which is what? D. Because it is A dot N is equal to the amplitude of A multiplied by the amplitude of N. What's the amplitude of N? 1. So it will be A N cosine theta. So A cosine theta is just D. Did you understand? So the equation of the line will be just R dot N excuse me, equal to D. Now, if R, vector R will be X in the direction of I plus Y in the direction of J plus Z in the direction of K, and N, the unit vector will be certain length L in the direction of I plus M in the direction of J plus certain distance N in the direction of K, and you dot product R dot N, this will give you what? L X plus N Y plus N Z, and this will be equal to D. And this is another representation for the equation of plane. Do you agree for this one? Okay? So what if the plane is now not defined by one point A and a perpendicular to the plane? If the plane has 3 points on the plane, can we still define the plane by those 3 points? Yes. How? This is what we will see here. So if we have a plane like this, and we have the origin is here, and we have a point here which is A, capital, with a position vector A, another point which is B with a position vector B, and a third point here C with a position vector C. So this is A, B will be what? B minus A, and then we will have, this is what? AC will be C minus A, and we'll have this one which will be C, and it will be C minus B. So if we have equation, this is second one, equation of plane defined by three points. A with position vectors A, B, and C. So if we start with point A, all points may be reached by moving a distance along each of the two non-parallel directions in the plane, whether it is B minus A, which is this one, or C minus A, which is this one. So those are two non-parallel directions. Yes, so if you cover the whole plane, how you will cover the whole plane? So let's assume that you can move from here to here along this direction, yes? And then you can move from here to here along this direction. As if you are, do you know the plotters, two-dimensional plotters, when they want to define any points in the plane? So if you have two non-parallel lines in the plane, you can cover the whole plane. Yes, because you will be moving from here to here across this one, and from here to here across this one. So if you get this one and you move it anywhere here, so you will cover this direction, and then if you fix this direction here and you move from here to here, you will cover the remaining direction on the plane. So what the equation will be in this case? The equation will be any point R on the plane will be just equal to vector A plus certain lambda multiplied by B minus A. So you take certain direction. So you start at this point, and then you take, let's say, lambda, you are here, for example, and some mu from this direction. So any segment from here and segment from here, plus the point that you started from, you will reach to the point R. So R will be, let's say, any points here. Let's assume that R will be any points here with this position R. It's a little bit complicated, but this is the representation. So lambda and mu are just scalar quantities. So we can just expand this one, and we'll reach to R equal to the vector A multiplied by 1 minus lambda minus mu plus lambda in the direction of vector B plus mu in the direction of vector C. So we can call this one alpha, and we can call this one beta, and we can call this one gamma. So the vector R will be just alpha in the direction of A plus beta in the direction of B plus gamma in the direction of C. So this will be the definition of any line with 3 points on the plane, the equation of the plane with 3 points on the plane defined by the position vectors A, B, and C, where the summation of alpha plus beta plus gamma equal to 1. Just sum here. 1 minus lambda minus mu plus lambda, lambda will cancel with lambda, and plus mu, mu will cancel with mu, and you will lift up with 1. Any questions so far? Okay. So now, let's take an example. So the example says that we want to define the line of intersection, define or find line of intersection of 2 planes. The first one is x plus 3y minus z is equal to 5, and the other one is 2x minus 2y plus 4z equal to what? 3. Okay? 2 planes. So let's assume that the 2 planes will be something similar to this. This is the first plane. And this is the second plane. Okay? So 2 planes, and this is the line of intersection, and we are interested in finding this line of intersection. Plane 1 will have a normal N1, and plane 2 will have a normal N2. Now, from this definition here, I just give it to you. R dot n equal to d. If r equal to x, I, y, j, z, k, and n, normal is li, m, j, n, x. And if you dot product both, this will give you lx, my, n, z multiplied by d. So from the equation of the plane, the components of I will be just what? L, M, and what? And N. So what's the equation for the I1, for the normal N1? This is the equation for the normal N1. L, M, N. Yes? So what's the equation for N1? It will be 1 plus 1 in the direction of I, plus 3 in the direction of what? J, minus 1 in the direction of K, and N2 will be 2 in the direction of what? I, minus 2 in the direction of what? Plus 4 in the direction of what? Okay. Do you think they are parallel? No. Why? If they are parallel, you will see here is, let's say, 1 minus 1 and then plus 2. Yes? If they are parallel. Yes? They will have the same proportion in IJK. They do not have same proportion in IJK. So definitely N1 is not parallel. Not parallel with N2. So if they are not parallel, what does it mean? N1 and N2 are not parallel. So they should intersect. The plane should intersect. The planes are not parallel. Because if N1 and N2 are parallel, the planes are also parallel. Here is a plane. Here is the other one. Yes? And if N1 is here, N2 is here, and they are parallel to each other, the planes are parallel. But in this case, if they are like this, so N1 and N2 is no longer parallel, so the plane should intersect. Did you get the geometry of this? So now we want to get the intersection. So these two vectors are not parallel, so the planes must intersect along some line. The direction for this line, we will call it P. So this line has a direction P. So let's move this guy here until we come to here. So this is what? N1. Then let's move this guy up to here. So this is N what? N2. Yes? Both intersect at the point B. So what do you think the direction of line P? Perpendicular to N1 and N2. So we should take the what? Cross product. Yes? So in this case, P is perpendicular to both N1 and N2. And we should take the cross product to be able to find out what's the direction of P. So the direction of P will be just equal to N1 crossed with N2, and in this case will be just I, J, K, 1, 3, -1, 2, -2, and 4. And if you do this, this will give you 10 in the direction of I, -6 in the direction of J, -8 plus 8 in the direction of K. Okay? If you want, you can just take P and dot product P with N1 and P with N2. What this would give you? If you dot product P with N. Look here. If you dot product P with either N1 or N2, will give you 0. So now let's look at the equation of sphere. So if we have a sphere like this, the center of the sphere, and this is the origin here, will be at point capital C. And if we have any points R capital at the surface of the sphere with a position vector R, what do you think this R minus C will be? Yes, so R minus C is just the radius of the sphere. So what's the equation of sphere? R square equal to constant, which is the radius. Yes? So in this case, R minus C all square will be just the vector R minus C dotted with itself, and this will be equal to A square where A is just the radius of the sphere. So after we study the equations of various geometrical objects like line and plane and sphere, let's go and do more analysis of how to use those vectorial equations to find distances if we want to calculate the distance from a point to a line, or from a point to a plane, or from a point to a sphere, and so on. So we will shift gears and define distances. So let's first look for the distance from a point to a line. So distance from point to line. So assume that, again, we have a line like before that passes through point A with a position vector A small, and the direction of the line is just B, and then we have a point P that we want to get the distance from point P to the line. So the position vector for this point B is just the vector, position vector B, and then this vector is nothing more than vector B minus vector A. Vector B minus A will give you this vector, and this angle is just theta. So let's assume that this distance, which is in this case the minimum distance, yes, from the point to the line, because the perpendicular usually will be the minimum distance from the point to the line. So D is the minimum distance from P to line, and P will be just the line direction, and A will be just the position vector of A and B. So this is A and B are the position vector for A and B. So the distance D is nothing more than P minus A, vector P minus A, dotted with or sine theta. So this distance in this triangle is just this sine this angle, but I have, in this case, I have to take the absolute value. Yes, so in this case this will be just the vector B minus A dotted with a unit vector in this direction. Yes, so we will call it B hat. So what's B hat? Any vector, if you want to get the unit vector, any vector, and I want to get the unit vector, it will be the vector B divided by the absolute value of vector B. If you have a vector 10 meters, and in this direction, what's the unit vector? It will be the vector 10 divided by 10. So it will give you a vector 1 in direction of what? In direction of this vector. Okay, so let's assume that we want now to calculate the distance from a line to another line. Instead of a point to a line, distance from between two lines. Okay, if the two lines are not parallel, the distance will be between the two lines will be what? 0. If they are not parallel, this means that they will intersect in certain position and the distance is 0. But if they are parallel, and this is a little bit tricky, let's assume that there is a vector here that goes into the blackboard, and this line is B. There is another line that come out from the blackboard. Okay, two lines. Let's assume that this is the first plane, and the first line is in this plane and goes inside, and this is the second plane, and the line goes out. So at the plane of the blackboard will be this is the plane, the first plane, the second plane, and the first line goes like this, the second line goes like this. At the plane here will be the perpendicular distance between both. So let's assume that this is the perpendicular distance between both. The origin is here. If we have a position vector for point B, which is P, and another point here on the other line Q, so the position vector will be Q. So this is what? P minus Q. And this is the unit normal to both of them. So in this case, what's the direction for the N? What's the direction of N? So here it is. Here is the two planes, and the first line just goes like this. The second line goes like this. Okay? So here is the two planes. One line goes in this direction. The other line goes like this. So let's assume that they are like this. So if you take the cross product of this with this, so how to get the cross product? You go from here to here, yes? So, and this is what? The perpendicular, which will be the N. So if you take P if you take vector A crossed with vector B, and then divide by the absolute value of vector A crossed with vector B, this will give you what? The unit vector perpendicular to both plane. So the equation D, this is the distance D, is just D will be equal to the absolute value of P minus Q. What's P minus Q? So let's assume that the two lines, one is here and one is here, and those are the two lines. Okay? So if you have a point Q here and a point B here, so what's the line joining between both? It would be something like this. So if you dot this with N, it will give you what? D. If you dot this line connecting both of them on the normal direction, will give you D. So when you dot this with N, this will give you what? D. The representation is a little bit difficult. So now let's look at the distance from a line, a point to a plane. So we got the distance from point to line, distance between two lines, distance from point to plane. Again, here is the plane, and we have a point A, is a position vector A. We have a point here, P, with a position vector P. And we want to get this distance, which is in this case D, and this is the normal to the plane. So this is what? This vector? This is A, and this is P. So A, so this is P minus A, this vector. So the distance D is just equal to P minus A dotted with what? N. Yes, because it will be this triangle, P minus A dotted with N. Did you understand? Now, how will we get the distance from a line to plane? So we get distance from point to line and line to line, and then point to plane and line to plane. So let's assume that this is distance from line to plane. So here is a plane and here is a line. The distance from line to plane. If the line is not parallel to the plane, the distance is 0. They must intersect anywhere. But now, in order to get the distance while it's not 0, let's assume that we have the origin and we have a point A on the line. The direction for the line is P. We have a point on the plane which is B capital. The direction for this B capital is P. And now we want to get this distance, which is D, and the unit vector again is normal here, N. So what's the equation for the line? Equation for the line is just R equal to A plus lambda multiplied by P. We just stated this a couple of minutes ago. So if N is the normal to the plane, then the minimum distance from the line to the plane is 0. This distance will be 0 if the line intersects with the plane, unless P dotted with N is equal to 0. What does it mean? P dotted with N is equal to 0. P is parallel to the plane, because this is in this direction, N is in this direction. Dot product, when it is equal to 0, cosine is 90 degrees. So this is the only case that we can find the distance D other than 0. So in which case D will be just A minus R, the vector A minus R. Where is A minus R? Is any point in the plane. In this case, let's say assume it's RB dotted with N, and this will be the distance. So let's assume that this is A minus R. So we will conclude with reciprocal vectors. So if we have two sets of vectors, those two sets of vectors are called reciprocal. They are the inverse of each other. So reciprocal vectors, if we have A, B, and C, and we have A prime, B prime, and C prime, two sets of vector. If they meet the condition that A dot A prime will be equal to 1, and this will be equal to B dot B prime This will be equal to C dot C prime. It's like 2 and 1/2 in just mathematics, arithmetics. 2 and 1/2, 3 and 1/3, 4 and 1/4. If you multiply both of them, this would be the reciprocal of the. But this is the reciprocal of the vector now. It can be shown that the reciprocal vectors are given by A is equal to vector B crossed with vector C divided by A dot B crossed with C. And of course, A dot B crossed with C should not be equal to 0, otherwise this will be indefinite quantity. And vector B is the same, C crossed with A divided by A dot B crossed with C, and vector C prime will be equal to A crossed with B divided by A dot B crossed with C. So what does it mean? A dot B cross C equal to 0. If you remember from last lecture, when we have scalar triple product, and I told you that if A dot B cross C is equal to 0, they are coplanar. Because why? B cross C will give you a vector. When you dot product another vector with this vector and it is 0, this means that that product equal to 0 when what? When cosine theta is 90 degrees, but this vector is perpendicular to A, B, and C, so A should be in the same plane with B and C. So if it's equal to 0, it's coplanar. This is not equal to 0, by the way. If it's not equal to 0, they are not coplanar. Not coplanar. And if A, B, and C are mutually orthogonal unit vector, in case that we have a mutually orthogonal unit vector, like I, J, K in the Cartesian plane, so if A, B, C are mutually orthogonal unit vectors, then A equal to A and B prime equal to B and C prime equal to C, and this is what we call identical system. Like if we have I, J, K, X, Y, Z, they are perpendicular to each other. So when you get this, so you will notice that A prime, yes, equal to B. Let's take an example. A prime equal to B cross C divided by A dot B cross C. Yes? So let's assume that A is equal to I, B is equal to J, and C is equal to K. Substitute here. A prime, we'll call it I prime. So I prime is equal to B. What's B? J. Crossed with C is K. Divided by A. What's A? I. Dotted with B, J. Cross what? K. J crossed with K will give me what? I. So this will be what? I. And J cross with K is what? I. I dot I? 1. So I prime equal to I. That's it. So this means that for mutually orthogonal unit bases, base vectors, if the 3 unit vectors are mutually orthogonal and they are unit vectors, you cannot differentiate between the reciprocal vectors and the vectors themselves. So they are identical. Did you understand? Do you have any question? We are done for today. See you next Wednesday.